So let me use this old-fashioned device. The inspiration for this talk came from two sides. First, applications to the dynamics of tornadoes, and mainly maybe on dust devils, which I was more focused in my professional life, and I will try to show some slides later on. And of course, the second motivation came from the side of theory, from the side of theory of helicity, and my attempt to develop, to extrapolate the notion on the Rankine vortex onto the case of fluid baroclinicity. It means that I tried to construct some Rankine-like vortex models which have axial flow confined to the vortex core, and also the buoyancy force, which is collinear to the axis and also confined to the core. It means that I tried to construct some simple, very simple as possible, how it is written here, vortex models, Rankine-like, which are embedded in a Boussinesque fluid, but the surrounding fluid is neutrally stratified, so all the buoyancy effects are confined to the core. And this problem looks like simple, but it's difficult because it is a competing effect or some kind of competition between Bernoulli effect or Venturi effect, as you may like call it. So when you have some tube, for instance, and you have some constriction, that then you have acceleration of fluid and fall of pressure, and this effect competes with the hydrostatic effect because warmer fluid is lighter. So this what I will try to speak about. Now about the first part. So it's very beautiful picture of tornado, famous. It's from vortex verification of the origin of rotation and tornadoes experiment, and also a photo of mine, which I took in Chile in this January of 2009. So you see, but it only looks like so strong because if it passes through you, so for a person, you are only to close your eyes and keep your head. So it's just looking very so, but it's not so. So there are two characteristic types of dust devils, so-called rope type. It's narrow, tight vortex which expands very high aloft, and a vortex which seems much more stronger, but it's not as such, because here it's this vortex is hollow, and the vorticity is confined to these edges, to the walls of this vortex. So I will speak on this vortex, which is believably has a uniform updraft within its core and extends to large enough altitudes, as I talk. So it's really interesting. So sometimes in nature you can find balls, this vase type, and also accompanying this is very tight rope type vortex. It's a sequence of photos. It will be about so you see these are moving, and this is some car chasing vehicle which tries to, and so you see passing this vortex, and so then it's destroying. So this was so the motivation coming from nature. And now some theory. So momentum equations in Boussinesque approximation, it's solenoidal velocity field. So if you consider in polar cylindrical coordinates r, phi, z, and assume that no dependence on phi on the azimuth, then you can construct nonlinear thermal wind equations, so equations which basically relates the azimuthal component of vorticity and buoyancy, and you can obtain two integral theorems. So it's like first momentum and second momentum. And so this is rather famous. So it expresses, it's two means of writing the pressure deficit in the vortex center. So this is hydrostatic effect, and this is, in a sense, so it's pressure depletion, and this is equalized by centrifugal force or centripetal acceleration. And this is additional term coming from nonlinear terms. And this equation is less trivial. So I will show and I will claim that it is a special sort of helicity balance equation, but for this specific case of steady axisymmetric flows. And so this term in brackets, square brackets, is vertical flux of helicity, this model. So if you take a general equation of balance of helicity in a Boussinesq fluid, you can write it in a somewhat eclectic form. So you can eliminate strictly pressure, which is always not easy to compute because you are to solve Poisson equation. And so to write this term, it's a partial derivative with respect to time. But for steady flows, it does not matter because it vanishes. It also vanishes when these terms, these two vectors are parallel. And so you have really this flux of helicity. So, and if you, for instance, are interested with a vertical component of this flux, this term vanishes because B is also directed vertically. And for ideal fluid, it's 0 as well. So you have only the vertical component take of these first two terms. And they just exactly can be so put in this term after some arrangements. So now about some self-similar vortex solutions. So the idea was to generalize this ranking-like vortex, but in the simplest way. So to assume that at each altitude, this vortex has the same profile as the ranking vortex. But of course, the radius of maximum winds changes with height. And it was also assumed that this vortex height or radius monotonically increases with altitude. So in this case, you can arrive at this equation, nonlinear equation, which relates the shape of the vortex, which is codified in this variable zeta. It's a reciprocal of maximum of radius of maximum winds. So Q is volumetric flux through the vortex, constant, and gamma is axial momentum. So it's Kelvin circulation divided by 2 pi. So this is integral from z to infinity. So in these equations which I showed, I took z plus its infinity and z minus as a current limit of. So it is really a writing of this equation. So this equation has the simplest possible solution when this term strictly vanishes. No. In this case, you can take this, substitute this, and calculate the buoyancy field which supplies or provides such a vortex flow. So here it's a sketch of this vortex. So you have this uniform updraft flow, this vortex which radius expands with height. So you have this limit, horizon. So this vortex has some upper limit. But formally, it can extend below, down to infinity. But actually it cannot, because if you compute the
maximum velocity at some level, and I will say few words how I choose it. So you see, this is helical parameter. It's reciprocal of the spheral parameter. So it's ratio of the mean updraft velocity to the maximum rotational velocity. So alpha must be always less than unity. So in fact, this solution has to be restricted because due to constancy of the volumetric flux and axial momentum, both vertical velocity and the maximum velocity rotational, they increase. But the axial velocity does it much faster because it's a square of radius, inverse square of radius. So this top level exists. But before this limit exists, this vortex must experience breakdown. And so actually cutting this vortex at the level of breakdown. So this vortex solution is restricted between this horizon and the breakdown level. So, and to choose the breakdown level, I used the condition so that alpha squared should be less than 1/2. I will show some slides a slide later. So, and greater than 0. So an estimate follows. So Vm squared must be less than this combination. It's like very well-known Torricelli formula without coefficient 2, of course. And this 1/2. This combination is often taken as a thermodynamical speed limit. But in contrast to general considerations like thermodynamical ones, so here the height of the vortex is rather well defined. So it is the height of this horizon. So I think it is one of advantages of this approach, though of course such a singularity can cause some questions, as we will see it's below. And so for the given buoyancy momentum or buoyant momentum, the vortex is strongest when the Rankine-like swirling convective plume, so below this truncation level, is such that is in a sense it's weakest. So there is very smooth transition here, because if we take very strong vortex here, it will experience very strong breakdown, and the resulting vortex above the breakdown level will be broad. And so as a result, we will have a weaker vortex above the breakdown level. It's, in a sense, it's like in here, it's in the Carnot heat engine, where the maximum efficiency is when the process is ideal, reversible. So it's just example of vortex breakdown, how it happens in nature, but it's just for some illustration. So I want really to show. So these are some algebra. So it's constancy of the vertical momentum flux. So it's famous equation in terms x. It's a reciprocal to alpha helical parameter. So x is actually sphere number. So to conjugate skates, and so the critical value when this x1 is unity. So these are two parameters helical below and up the breakdown level the same, and 1 divided by square of root of 2. So we get this condition of maximum strength. And second, next to the simplest, as I would say, example, when we have really a vertical cone. So we have a virtual source of mass beneath the Earth, and so expanding like in this picture. So this, so the flow is irrotational inside. So it's shown no flow outside. The radial profile of tangential velocity is again Rankine-like. So the same setup, but only another shape. So C is small parameter. So you again get this formula, which is morphologically similar to that for the vortex number 1, but only there was H minus delta. So D is some kind of analog or measure of vertical extension of the vortex. You can again truncate this vortex at the breakdown level and get absolutely the same formulas as above. And so this downward helicity flux, so for vortex number 2 it can be computed. So for the vortex number 1 it is nearly the same, but interestingly there is artificial and very weak flux. It's order of 10 minus 4 across the horizon due to this singularity. And also it's very interesting that the vertical energy flux is directly proportional to the helicity flux. And so this is scheme. So buoyancy production of helicity of energy, flux downward. So main dissipation of helicity and energy occurs at the breakdown level, but still some energy and helicity transports further to the ground. So the dissipation of helicity and energy occurs here. So it's both at the breakdown level and in the very last. So it's total helicity, and it can be expressed as a product of toroidal and poloidal circulations as it follows from not in agreement with Morpher's arguments, so it's also interesting. I have 1 or 2 minutes. 1 minute. And it's interesting. So if you use famous analogy with magnetohydrostatics, and you consider magnetic hole where gas pressure is 0 as the vortex center, and you can consider fully compressible atmosphere, it's polytropic. You can consider 2 cases when temperature decays with height and increases with height. And you can construct 2 solutions, which the polytrope value is 4 or minus 4. No, this modulus is minus 4. So you get exactly these 2 solutions. This is simplest, this is next to the simplest. So for this magnetic tension vanishes, and for this magnetic tension term does not vanish, but is proportional to the pressure term. Thank you. So the summary and
yeah, I don't understand how you can prescribe the buoyancy B as a function of Z. Wouldn't that itself depend on the flow? In other words, coupled with a diffusion equation.
Yes. In this work, I, in a sense, put the thermodynamic equation on the secondary position, because I assume the simplest as possible kinematic structure of the vortex, and then compute the buoyancy field, which can be computed is rather reasonable. But if substituted into the thermodynamic equation, it shows that one needs some diabatic forcing for supporting of these vortices. Basically, this is a diabatic cooling. So these vortices transport some excessive heat to the atmosphere. So this heat has to be removed. On the other hand, you may like to consider a diabatic vortex where there is no diabatic forcing. In this case, you can also use these equations to calculate the shape of the vortex. It allows. In this case, the qualitatively
the vortex has a shape similar to this hyperbolic shape, but it lacks analytical formulation. It's some transcendental function. So I choose to use the simplest formulation for the shape to be able to compute all these helicity terms, etc., at the expense of considering this rather complex diabatic forcing field for supporting such a simple vortex structure. So this buoyancy field can be computed. It's reasonable. It's quite reasonable. It corresponds to the warm core of the vortex with some jump of buoyancy at the edge and zero buoyancy in the periphery of the vortex.
One more question. Would it be easy to include a stratified internal wave radiation field?
Oh,
Well, you're just assuming a buoyancy at the top and at the bottom in a, say, sharp interface or a linearly stratified fluid. The interaction between internal waves and the boundary of the vortex say, could change the shape, probably.
Yeah, you know, using the simplest case when the surrounding atmosphere is neutrally stratified, because considering the stratified atmosphere provides some difficulties on this way. No, the only what I can do it, for instance, for the vortex cone, I can consider the generalized vortex, Rankine vortex, when the flow is not potential, but there is some exponent. But it still gives some difficulties because you are to have some self-consistent model. These two models are self-consistent. This is.
Thanks.
We'll move on to the next speaker. Thank you.